What up, Tali? Welcome. Here's a screencast for you. So, I was just talking about how today we're going to go over volumes. The first thing that there's 3 things due, but it's due next Monday. So it gives you some time this week. We should be able to I think we're going to finish all the notes pretty much. Oh my god. Alright, so let's go ahead and let's go to draw board. What's wrong?
What?
What? Are you talking to me?
No.
Oh, okay. Bye. Okay. Did I share this? I did. I think I did. 7.3 notes. Yes. Yeah, if you go to the chapter 7 on the right side with all the downloads, you'll see there's like section into 7.1, 7.2, and 7.3. Okay. Oh, do you need time to go print it? Yeah, just chill. I'll pause the screencast. So, lesson plan first, at the worksheet, review, like it's all this one packet. Kind of like the way of doing this. Maybe I'll do this in the future. Yeah, we'll see. Yeah, so it does kind of like, ideally you finish most of the 6.1, 6.2 homework this week, because we're going to pretty much finish most of the notes this week anyway, so. Okay, so definition, volume of a solid. So now we're in volumes. The volume of a solid of known integrable cross-sectionable area A of x from x equals a to x equals b is the integral of a from a to b. Okay, so what the heck are we even talking about? Alright, this should have a parenthesis. Alright, so if you think about it, let me draw a little solid, right? What if I have a nice little cylinder? And if I, you can take little discs of area, and if I take all these areas and add them together, I'll have my total volume, right? Similarly, I could have a nice little box here. Alright, and if I find the area of this box, I could keep finding lots and lots of slices, and I can go slice by slice. Right, here's another slice. I'm taking slices. I could be taking, right, these little areas. I'm just slicing, and I know how to find area. That was our last lesson. And so something cool I can do is I can say, okay, here's 2 functions. Find the area between them. And then what if I rotate them about this axis to make like a 3D object? So that's something that we do all the time. Not even being facetious, I'm not even joking. We do this a lot. Alright, so how do you actually find volume by this method of slicing? So the first step, sketch a typical cross-section. Very visual. It helps you figure out what the heck you're supposed to do. Then you find a formula for your area, right? So this area is how you find the area of your cross-section. All right, so if the cross-section is perpendicular to the x-axis, you do upper curve minus lower, versus if it's perpendicular to the y, right curve minus left. Okay, so this is from 7.2. This is what we learned in 7.2, how to find areas, right? If we have, I think you guys understand what I'm talking about. If I have, if the area, I'm trying to find like slices going this way, where it's perpendicular to the x versus perpendicular to the y if I'm taking slices like vertically. Okay, that's what it's talking about. If my slices are horizontal here and I'm slicing perpendicular to the y-axis. Yeah. Alright, and then find the limits of integration from what number to what number, and then I integrate a of x to find the volume. Alright, it makes a little more sense if we do it, that example. Right, a solid lies between the planes perpendicular to the x-axis. From x equals 0 to x equals 4. The cross sections, which are squares with bases in the xy plane, are perpendicular to the x-axis. Between these planes, run from y equals negative root x to y equals root x. Find a formula for the area A of x of one cross section, and then use it to find the formula of the solid. Oof, that's a lot. Okay, so first thing we're going to do is let's find, so you can see the cross section is going to be a square because we're going from y equals negative x to positive x. Alright, so let's zoom in a little bit so we can talk about that. Okay, so right here, this is the function, this is the graph of y is equal to negative root x. The graph up here, this other one, I'll do like dots so you can see a little better. This is the graph of y equals positive root x. So I'm going the same length on both sides, and it says that we're using squares. Okay, so to find the total length across, all I have to do is multiply this area by 2. And I know this length right here is going to be root x, so the overall side length is going to be 2 times root x. That's the length of my side. I feel like maybe I confused myself. We're good, right? Where it says the bases are squares, we know we're going from negative root x to positive root x. Okay, well, that means these two lengths are going to be the same. So I just multiply by 2, and then that's the total length, is 2 root x. Alright, so the cross-sectional area we have to find. Alright, so going back up, number 1, sketch a typical cross-section is sketched for us. Number 2, find a formula for a of x. So our cross-section, it's a lot of s's in a row. Cross section is going to be a square. It told us that. So our area of a square is just side length squared. Well, a of x here, we know a side length is 2 root x. So if I square it, the area is going to be 4x. Right? 2 squared is 4. Root x squared is just going to be x. So our area is 4x. Okay, so to find volume, we're going to take the integral from a to b of our area function times dx. So we are perpendicular to the x plane. Where does it say that? Perpendicular to the x-axis. So we're taking the upper minus the lower. Well, right, so if you take root x minus negative root x, you get root x plus root x, which is 2 root x. Okay, that's like a second way to find this area. Or, sorry, to find this length. Yeah. Anyway, we have our equation for our area. We're trying to go from 0 to 4. So we're going from 0 to 4. We have the function for area right here, so move that down. So 4x dx. So we're taking, let's see, so add 1 to the exponent, divide by a new exponent. So this is going to be x squared. No, sorry, 2x squared. Yeah, 4 divided, okay, 2x squared, going from 0 to 4. So plugging in our bound, I'm taking 2 times 4 squared minus 0, 16, so it's going to be 32. Can you guys see the little pop-up that just showed? Sorry to interrupt. Are you enjoying Drawboard? Nope. Nope. Get lost. Not right now. Of course I enjoy Drawboard. It gives me so much joy. Okay. Cool. So this is an interesting looking, like, shape. It's kind of weird shape. Alright, I think we're ready to go to the next one. I'll give you a moment. Take a drink of water. I don't think I even asked. I apologize. Did you guys have a good Memorial weekend? Hopefully you didn't have too much work. Alright. It's good to hear. I drove through Zion and Bryce on my way over to Nebraska, and it was crazy. Crazy how many cars there were. It's a bad idea. I shouldn't have done it. But it was just so beautiful, I couldn't help it. It's not like it was that far out of my way. Alright, use the same basis as example 1. Okay. And use the cross sections that are semicircles with diameters in the xy plane are perpendicular to the x-axis. Okay, so the difference is, instead of having these squares, I'm going to have like semicircles. Okay, that's the big, oh, I should erase that. So I'm going to be uploading these later. Alright, so that's the difference. We're using the same function, the same bounds. It's just going to be, instead of like squares, we're doing semicircles. So let me redraw this. Alright, so here's my x, here's my y. Let's see, my function. Wait, was it blue up here? I should use the same colors. I should just copy paste it. What am I doing? Whatever. Here. Here. This occurred at 4. I think that's what it said. Yeah. Alright, so that's the same picture as above. So here, we're trying to do semicircles. So if I could almost like, 3D up it, it's going to be like this red is the bottom of my semicircle, and then the black is a 3D. So if you can imagine it like coming out at you. So it's almost like a megaphone, except chopped in half. It's like a semicircle looking megaphone, so it looks something like this. Right, where these are like semicircles. Yeah, okay. I'm not an artist, never claimed to be. This is why it's so hard, because visualizing what the heck the problem wants, that's hard. Okay, so we know the area is going to be a semicircle. So the area of a semicircle, so remember that's a half circle, it's just going to be 1/2 pi r squared. Now the radius. So I want to know, the radius is going to be half this length. Well, half this length is going to be whatever our y is. So the radius is going to be our y value. So the function for my area is going to be 1/2 pi, well, the y value is square root of x squared. So the function to find area is just going to be 1/2 pi times x. Okay, let me explain why that is the case. All right, so the radius, sorry, this is an x equals 4, right? It's not saying the length, it's just saying that's where the red thing is. So remember, like this red line and this red line are the same thing. So the radius is just going to be whatever our y value is. It's whatever the height is, which is our y value. Right? The radius of this semicircle is going to be whatever the y value is. So I just plugged in the y value, which is root x. So root x squared is just going to be x. And then the last part, in order to finish this problem, find the volume. We're going to integrate area. So we're still going from 0 to 4, but it's a different equation because we have a different shape. Instead of squares, we're going to have semicircles. Dx. So let's see. Add 1 to the exponent, divide. So this is going to be 1/4 pi x squared evaluated from 0 to 4. So 4 squared is 16, divided by 4 is 4 pi. That is the area. The volume of the solid. The volume. Okay. Let's keep going. Elliot, are you still with us? Oh, okay. Sorry. I just didn't see you. I was worried. All right. Perfect. Yeah, for me, it's hardest like drawing the pictures and really understand like what is this looking like. So it's more difficult because I can't like, show you with my hands and like right in front of you. All right. A solid lies between planes perpendicular to the x-axis from -2 to 2. Cross sections, isosceles right triangles. I highlight the important parts. Blah blah blah. Base is the xy plane perpendicular to the x-axis, so it like tells us which way to go. So this is square root to 0. Find a formula. Blah blah blah. Okay, draw a picture. So if we have a square root of a number minus x squared, this is a semicircle. Let me draw this out. And we're going from -2 to +2. Okay, so I'm going to let this guy be blue. So here's -2, here's +2, and we know this is a semicircle. It will go up to a height of 2. Okay. Then our second function is y equals 0, so that's just the x-axis. So this is the function. Alright, and we are going perpendicular to the x-axis. So that means we're going upper function minus lower function. So we're taking slices in this direction, and it's going to be triangles. So this is a really weird looking shape. So we're perpendicular to the x-axis. Let me draw my colors. I should make this green instead. So this is a slice. Alright, so this is my height, and my height is the function root 4 minus x squared. And it's isosceles triangle, so the height is the same as well. So isosceles mean these two have the same length. So if you can kind of imagine, like there's this triangle here, like 3D triangle. It's kind of hard to see because I'm slicing it this way. If I was looking, oh my gosh, can I even do this? Okay. So I have here, that, the, cha, 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 cha. It's really hard to draw this. I'm sorry. No wait. It's gonna be isosceles triangle. So start small, gets bigger, gets smaller. So it's almost okay. So this is really hard to draw. It's almost like a piece of an orange. You know what I'm talking about? Like if you take a little slice of an orange, like this guy, how it's like a wedge almost. It kind of looks like a wedge. That's what I'm trying to draw here. Is this like piece of a wedge-ish thing? Oh man, I'm really not an artist. I'm sorry. As long as we understand it. Oops, I want to delete this. Okay. Okay, so if you peel an orange and you take a little slice of the orange or a slice of an apple, oh, that's not what I want. It's almost like a, oh my god, kind of like, I can't draw visually because those are isosceles, roughly isosceles right triangles. Like a single slice wedge of an orange where it's like curved. So you have the curve, but then like it's smaller, bigger, 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 height, smaller, smaller, smaller. Yeah, something like that. I really need to do a better job being an artist. Okay, so that's enough time wasted on that. Oh, I erased my slides. No, go back. Yeah. So this green is showing you like, this is where the blue part hits. This is where the red part hits. Yeah. Okay. So to find area, area of a triangle is 1/2 base times height. Well, that's just going to be 1/2. My base and my height are the same thing, so I'm just going to take root 4 minus x squared and square it, since base and height are the same thing, because it's isosceles. So this is just 1/2 of 4 minus x squared. So that is my a of x. That's my equation for area. And then to find volume, we're going to go from -2 to 2, because it told us our bounds. We're going to take our equation for area and integrate it. So this is something you would plug into your calculator. So you get 5.333, because you get like x cubed over 3, no, over 6. 2 minus x cubed over 6. Ugh. So plug into calculator. So this is showing the setup and etc. I think this is the last page of notes that I scheduled to do for today. Well, we have one more, yeah. The circular cross sections. Whew, okay, we got this. So what we've been doing is we've been taking like slices, slice, and then we determine what the shape of our slice is going to be. Now we have like circles as our cross section. So not semicircles, not squares, not triangles, but circles. So in the cross sections are circles, the area for our area changes because these are solids of revolution. So if you can imagine revolving this around the x-axis, or have you guys ever, I don't know, decorated, maybe I think you're both like super into either Stuco or different clubs or something. You know those like little balls that you can like decorate with where they're like flat and then you unfold them? It's like a bunch of paper. Right. So that's like a solid of revolution. So imagine this guy right here is one of those pieces and you can like unfold it and twirl it around. Right? You're revolving it around the solid. That's more or less what happened. You're just taking it and like revolving it in 3D, turning it around. So these are solids of revolution because you're literally revolving them around an axis. So normally area is pi r squared, where our r here, our radius is going to be our y function. So if our volume is just going to be pi times the integral from a to b, from where we start to end, of the radius squared dx, where the radius is our function. Let's see. Is there really anything else I want to say about that before I do the problem? Because normally pi times my function squared dx, well, if you have a constant and you're taking an integral, you can move the constant outside. Like that's how we got this. You just move the constant out front. Okay. I don't think there's anything else I want to say about that one. This is, I think, yes, this is the last problem we'll do today. And then you can work on your homework or whatever. Alright, so the region of the graph between f of x equals 2 plus x cosine x and the x-axis over the interval is revolved around the x-axis to generate a solid. So the issue is, I'm not just taking I'm not using this as like doing, oh my god, I can't even talk. So I'm not like doing squares of this, right? Doing little squares and making it 3D. I'm literally revolving this around so it's nice circle, because it's a solid. Right, we're not doing vases yet, so they're not hollow. This is solid. Okay, so we need to find the area. So this is revolved around the axis. So we know the area is pi r squared. Well, r here is our function. So this is just going to be a of x. The area function is going to be pi times. All right, and then our function 2 plus x cosine of x, and then squared. I'm just going to leave it like that. All right. I think I explained that because the radius is just going to be whatever my function value is, because that's how I find the height is the y value, which is our function. So to find the volume, we take pi times the integral. We're going from -2 to 2 times our, let's see, pi times our radius. Our radius is 2 plus x cosine of x, and then radius squared, because pi r squared is area, so our radius is squared, dx. And then you have to, I'm not going to do this one. I'm going to plug it into the calculator. So plug into calc. So if you do that, you get 12.429. Okay, so we talked about all sorts of shapes today. That was the general introduction. Let me make sure. I'll be right back. Rectangles, squares, semicircles. Okay, all of this is from what we did today. All the things are due on the first. Okay. And then everything, I'm pretty sure all of this, I think all of this is what we're doing tomorrow. We'll see. So I'll go back down. You guys have another 17 minutes. You could work on Khan Academy if you want. Disk, 3. Okay, cool. Yeah. Oops. Okay, cool. Any other questions before I set you guys free? Okay, I'm going to end the screencast.